Okay, so far we have talked about normal stresses, so either tensile stress or compressive stress. So tensile stress is yung force is away from the object or from the face of that object being considered, and compressive is towards the object. Okay, so both are normal forces na tinatawag. Okay, in both cases, perpendicular yung force, whether compressive or tensile, doon sa face, okay, nung pinag-a-applyan mo nung force or stress. Okay, but let's say, if you have this object right here, in yung force ay, let's say, parallel dun sa area. Okay, you have here, in this example, two opposing forces applied parallel dun sa surface. Okay, in that case, deformation will be such that, okay, magiging ganito yung tsura, okay, in this figure right here, and there will be an angle theta, okay, which is a measure of the strain. So we call that shear stress. So force over that applied area or area of application is the shear stress. And if normal stresses are given the symbol sigma, right? Small letter sigma, so shear stress tau. Okay, and to distinguish from normal force like compressive force or tensile force, we use the subscript S, no? F sub S. Ganoon din naman si area A sub S. Yun yung shear stress. So kung may shear stress, paano naman yung shear strain? So di ba si strain kay normal stress, right? Yung strain na alam natin, it's simply yung elongation divided by the original length. So ganoon din naman kay shear strain. Okay? And to distinguish it from the other strain, so we will also use S. Okay? So that will be elongation, okay, or deformation divided by the original length. And that is, it turns out, it's equivalent to tangent of the theta right here, yung this angle. Okay? So kung merong Young's modulus, meron ding shear modulus, and we use G, di ba si Young's modulus, letter E, yung symbol niya. Si shear modulus, letter G naman, it's stress over strain, but in this case, shear stress over shear strain. So substituting FSAS over delta S, deformation, no, over the original length, and rearranging, therefore, to compute for the shear deformation, you'll have this formula. Okay. Now, another thing is your Poisson's ratio. So what is this? You have here, let's say, an object, okay, and you're applying two opposing forces, okay. So what will happen is that this object will, of course, elongate. Like that. Now, nung ilelongate mo yan, okay, ang nangyari, humaba siya, of course, so it will have a deformation, okay. Pero yung kanyang kapal, no, ay nagbago din. So kanina, ang kapal niya is like this. Ngayon, nagbago yung kapal niya. So, bumaba yung length niya, pero bumaba naman yung kapal niya. So, the ratio of that lateral strain and the longitudinal strain is what we call your Poisson's ratio. Okay? And if the Poisson's ratio is equal to 0.5, exactly, no, the material is said to be incompressible. Okay? And since we know how Poisson's ratio is computed, we can actually derive the relationship between the Young's modulus, the shear modulus, and the Poisson's ratio. So if you know your Young's modulus and Poisson's ratio, okay, you will be able to calculate the shear modulus like that using this equation. Okay? And another formula that may be of use for you is what we call your modulus of volume expansion, or K, no? Or we call that also bulk modulus of elasticity. It's a measure of a resistance of a material to change in volume without change in shape or form. And it's given by this equation right here. Just a few more terminologies that we need to understand. So if a material is of uniform composition, okay, we call that material homogeneous. Okay. Otherwise, kapag non-uniform yung composition niya, it's heterogeneous. Okay. Now, you have also here your isotropy. Now, if you have identical values of a property in all directions, in other words, wherever you look at, okay, north, south, east, or west, okay, and the property it's always the same, we call that material isotropic. Okay. Otherwise, kapag nagbabago yung properties depending on the orientation of the body, we call that anisotropic. Graphite is an isotropic material. So let's say you're here. Anywhere you look at, doon, dito, 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 or whatever orientation you put into your object, okay, on graphite, or it may be even diamond, okay, that is called isotropic because the properties will be identical in all directions. While wood and bone are some examples of anisotropic materials. Okay? So, kasi si wood, okay, iba-iba. Punta ka dito sa direction na to, medyo mas weak in terms of modulus of elasticity compared sa ibang direction, and so on and so forth, right? Even your bone, depending on the molecular internal arrangements, okay, iba-iba sila depending on where you look at, okay, ng mechanical properties, and that's your anisotropy. Okay, so let's have this example. You have, let's say, a small cubic tissue specimen with dimension h equals 1 centimeter. Okay, this is cube, so it's all 1 centimeter length with height. And we are testing this material to determine its elastic properties. Okay? Now, let's assume that the material is linear, isotropic, and homogeneous. Okay. If the material is compressed, okay, by 5%, so you see the arrows here, these are forces that will compress the material, and the material is compressed by 5%. Okay, 5% of the initial height. And remember, the initial height is 1 centimeter. And we're going to also assume that the material is incompressible. Okay? Remember that when we say incompressible, the Poisson S ratio is 0.5. The question is how much force would need to be applied. Okay. First, you're given what? 5%. So anong ibig sabihin ng 5% na yan? Where's my pen? Okay, ito. So 5% means that's the strain. Okay? 5% yung gaano mo, how much did you compress the material. So basically, that 5% is your strain. Okay? And the Poisson's ratio is 0.5 because we assume here in letter A that the material is incompressible. Okay. Next, we are also given here that the Young's modulus is 1 megapascal. Okay? So, remember that the Young's modulus is stress over strain. Okay? Stress is F over A. Strain is like that. Okay? It's basically the deformation divided by the original length. And we know that to be 5%. If we're going to solve for A, we arrive at this. F equals the modulus of elasticity times the strain times the area. Okay, so it's just basic algebraic rearrangement of your variables. Now, you have to substitute the given. Okay, where's my... All right. So the modulus of elasticity is 1 megapascal. Strain is 5%. Area is 0.01 square meters. Okay, yung area ng isang face. 0.01 raised to 2 rather. And the force is 5 Newton. Okay. Next, following letter A, next is that a shearing force is applied. Okay, this is after you apply the normal compressive force. What is the shear modulus? Okay. We're looking for the shear modulus based on your measurements in A and the stated assumptions. What are the stated assumptions in A? That the material is incompressible, that we perform an experiment such that we are compressing the material by 5%, and all other assumptions. Now the question here is how great a shear force would need to be applied to displace the top surface a distance of 0.1 h. So, ano ibig sabihin nun? Di ba ito yung specimen natin kanina? We have compressed this already by 5%. Now, gagawin natin, you will now again apply a shear force. And if we're going to apply that, ang sabi, this top surface here, okay, will be what? Displaced by a distance of 0.1 h. So, di ba, h yung kanyang unang size, okay? H is 1 centimeter. You will displace that further by 0.1 centimeters. Okay. So, 0.1 h or 0.1 centimeter, kasi 1 centimeter lang naman yung h, is your deformation. It's not the strain, but rather the deformation. Deformation is how much siya nag-elongate. Yung strain kasi yung percentage of elongation. So therefore, ang percentage of elongation is 0.1. Or that's 10%, right? 0.1. Since we are following experiment A, wherein the assumption is that the material is incompressible, and also we know the value of the elastic modulus E. Remember from our discussion a while ago that there's a relationship between the shear modulus, the Young's modulus, and the Poisson S ratio. So what we want to get here is the shear modulus. And to do that, just use this formula. E is 1 times 10 raised to 6 pascals, 2 times 1 plus Poisson's ratio is 0.5, and you will arrive at 333 pascals. Now, remember that your shear modulus is shear stress over shear strain. And shear stress is Fs over As. And then you have your shear strain. If you're going to solve for the shear force, okay, you will arrive at this relationship. And we know G already. The shear strain is 0.1. And the area is still 0.01 squared. So your shear force should be 3.33 Newton. Okay. And lastly, what if in the process of conducting the experiment in A, it is observed that the lateral dimensions of the specimen increase, okay, from H to 1.02 H. What is the final volume? And we will determine the Poisson's ratio and whether the specimen is compressible or not. Remember, ito yung original na dimensions ng specimen natin. What we did is we compress it na naging ano siya, 0.95 H na siya. From H to 0.95 H. Why? Kasi diba in letter A, we compress it by 5%. Now in that process, the lateral dimensions increase from H to 1.02 H. Kanina H din to, yung lateral dimension niya, sorry, H, naging 1.02 H. Kasi nag-compress ka dito, so lumiit, humaba naman yung lateral dimension. So what will be the final volume? If the initial volume is H cubed, right, because it's a square, so therefore the initial volume will be 1 cubic centimeters. But in this new compressed material here, the final volume will now be, let's say, yung H dito, yung what is this, width, right? Hindi nagbago. Ang nagbago yung lateral dimension, naging 1.02 H na siya. And then yung height niya, naging 0.95 H na. So that will become 0.969 H cubed. Okay? Or 0.969 cubic centimeters. It looks like it's compressible material kasi from a volume of 1 cubic centimeter, naging 0.969 na lang siya. So let's check how by doing or calculating the Poisson S ratio this time. Okay? Lateral strain over longitudinal strain. Ang lateral strain is 0.05. Tama? Kasi 5% yung decrease. Longitudinal strain is 0.02. Kasi 2% yung increase in the lateral dimension. So the Poisson S ratio is 2.5 and therefore the material is incompressible. It's compressible. Okay. So next is we're going to discuss now if your material is exhibiting viscoelastic properties. So we have covered elastic properties. Now what if the material is exhibiting both viscous behavior and elastic behavior?